In lesson 5.1, we're going to talk about fundamental identities. An identity simply is an equation that holds true for any value of x that we put in there. Okay, that equation is always going to be true. In trig, there is many identities. Okay, so we're going to go through the main ones and use these to simplify and rewrite problems in a way that is much easier to solve. So some of the first identities, okay, I'm not going to require you to write these down in your notes. You can go on Google and search trig identities and find a PDF document that has all of the different identities on there. If you would rather write these in by yourself in your notes, that's perfectly fine as well. Okay. First one, reciprocal identities. We've already talked about this in the past. We know sine corresponds to cosecant, cosine corresponds to secant, tangent corresponds to cotangent. They're just reciprocals of each other. The quotient identities at the bottom, we've already talked about tangent. We know that's sine over cosine. Cotangent is just a reciprocal of tangent, so it is cosine over sine. One of the most common identities we're going to use is the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Okay. Yes, that involves using the Pythagorean theorem to come up with that identity, which is thus where the name comes from. Okay. The other two we don't use necessarily as often, but we still need to know them and apply them. Now I'm going to show you how we go from our main Pythagorean identity and get this identity. Okay. So if we start with sine squared theta plus cosine squared theta equals 1, I'm going to divide this whole equation by cosine squared theta. Okay. So if I take sine squared theta divided by cosine squared theta, sine over cosine is tangent, so that first term is going to be tangent squared theta. Cosine squared theta divided by cosine squared theta, anything divided by itself is just 1. And 1 divided by cosine. Remember, cosine corresponds to secant, so 1 over cosine is secant squared theta. So that is where one of those other Pythagorean identities comes from, taking the base one and dividing everything by cosine squared theta. So now, if we would divide that whole equation by sine squared theta, alright, this is going to give us that third Pythagorean identity. Sine squared theta divided by sine squared theta is 1. Cosine squared theta divided by sine squared theta is cotangent squared theta. And 1 divided by sine, remember sine corresponds to cosecant, so 1 divided by sine squared theta is cosecant squared theta. So that's how we come up with those other two Pythagorean identities. The other two types of identities we're going to talk about in lesson 5.1, cofunction identities and even odd identities. I would say these ones are probably used less often compared to the first three different types of identities we talked about, but we're still going to use them. Okay, so take a look at these, write these down in your notes, and we will use these to rewrite and simplify some problems moving forward. First example, we want to find sine of theta and cosine of theta if we know tangent of theta is equal to 5 and cosine of theta is greater than 0. Okay, we could use a reference triangle like we did in lesson 4.3. We know cosine is positive, so we must be in quadrants 1 or 4, and if tangent is a positive value, we know we're going to be in quadrant 1. Okay, so we could go through that same process to solve this, but now we're going to learn how to use trig identities in order to find those values. Okay, and using trig identities, you have to be very creative when trying to solve these problems. So I'm going to use one of the Pythagorean identities. Secant squared theta is equal to 1 plus tangent squared theta. Okay, the reason I'm going to use that, we know what our tangent value is. So secant squared theta is equal to 1 plus If tangent of theta is equal to 5, this becomes 1 plus 5 squared. Okay? And we know 1 plus 5 squared gives us 26. So secant squared theta is equal to 26. It's secant by itself. I'm going to take the square root of each side. And I'm left with secant theta is equal to plus or minus radical 26. Okay, you're probably wondering, why am I using secant, finding the secant value if I'm looking for sine and cosine? Well, secant is related to cosine. It's the reciprocal of it. So, I know cosine of theta must be equal to 1 over plus or minus radical 26. Okay, because cosine and secant are reciprocals, we know secant is plus or minus radical 26. Take the reciprocal of that, and we get cosine of theta. Key part, we know cosine of theta must be greater than 0, so our end result is 1 over radical 26. We're going to ignore that negative value because cosine can't be less than 0. So now we need to find the sine of theta. Before we talked about one of the quotient identities, tangent of theta is equal to sine of theta over cosine of theta. Okay? And we know in our problem tangent of theta is equal to 5. So we can set sine of theta divided by cosine of theta equal to 5. Well, if I want to get sine of theta by itself, I would multiply each side by cosine of theta. So sine of theta is equal to 5 times the cosine of theta. And we just found that the cosine of theta is equal to 1 divided by radical 26. So we have 5 times 1 over radical 26, which is equal to 5 over radical 26. So we have our sine of theta and cosine of theta. Those are the same two values we would have found if we used a reference triangle to find those values. Example 2, if cosine of theta equals 0.34, we want to find the sine of theta minus pi over 2. In this problem, we're actually going to have to use two different trig identities. First identity we're going to use is knowing that sine is an odd function. So we have to use that odd identity, which means if we take the negative of everything that's inside the parentheses, so if I have sine of, I'm going to make everything the opposite sign inside the parentheses, so we have negative theta plus pi over 2. If we do that, sine becomes negative out in front. And that was our odd identity. If I just want to simplify this a step, the opposite of sine, rewrite these terms inside the parentheses, we can write that as pi over 2 minus theta. Now we're going to have to use the cofunction identity. If you look back at the cofunction identities, the sine of pi over 2 minus theta is equal to cosine of theta. So we can simplify this to the opposite of cosine of theta, and we know the cosine of theta was equal to 0.34. So the sine of theta minus pi over 2 is going to be equal to minus 0.34. So we had to first use our odd identity, then a cofunction identity. Example 3, we want to simplify sine cubed of x plus sine x cosine squared x. Okay, right now this looks really complicated, but this simplifies down to a very nice value. Okay, so first thing we should do, if we have multiple terms, see if there's anything they have in common. If we look, both of those terms have a sine x in common. So if we take a sine x out in front, our first term, that was sine cubed x, if we take a sine x out of that, we're going to be left with sine squared x. Our second term, sine x cosine squared x, if we take a sine x out of that, we're left with cosine squared x. right? So factoring out a sine x, what they have in common. Now, this is one of our Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. Sine squared x plus cosine squared x is equal to 1. So this simplifies down to sine x times 1, which is just sine x. So that really complicated expression we started with simplifies down using trig identities all the way to just sine of x. Example 4, we want to simplify the quantity of secant x plus 1 times the quantity of secant x minus 1, all of that divided by sine squared x. Again, something that looks really complicated, but is going to simplify down really nicely. In the numerator, we have two binomials being multiplied. We could use the FOIL method, or if you recognize that this is a difference of squares, you can multiply really quickly. Okay, secant x times secant x is secant squared x. If we FOILed, we'd have a positive secant x and a negative secant x. Those would cancel out, so we can ignore the middle terms. 1 times negative 1, negative 1. Okay, all divided by sine squared x. The numerator, secant squared x minus 1, is one of our trig identities, one of our Pythagorean identities. That is equal to tangent squared x. Okay, divided by sine squared x. One strategy when trying to simplify these problems is to always write our trig terms in terms of sine and cosine. So that means in this problem, we're going to want to rewrite tangent in terms of sine and cosine. We know tangent squared x is the same as sine squared x over cosine squared x, and that is being divided by sine squared x, which we can write over 1. So now we have a fraction divided by a fraction. We can take that fraction and multiply it by the reciprocal. So we have sine squared x divided by cosine squared x, multiplied by the reciprocal, 1 over sine squared x. And we get a numerator and denominator to simplify. So that is 1 over cosine squared x. Okay. The last thing we're going to use is one of our reciprocal identities. Remember, cosine is related to secant, so 1 divided by cosine would simplify to secant squared x. So starting with that really complicated expression in the beginning, that all simplified down to just secant squared x. Example 5, we want to simplify cosine of x divided by 1 minus sine x over cosine x. Okay. Another strategy you might want to try when we have two terms, two fractions that are being added or subtracted, we need to write that as 1. So to combine these into one fraction, we need to get a common denominator. So if we look at the first term, cosine x over 1 minus sine x, we need to multiply the numerator and denominator by cosine x. So if we do that, this is going to be equal to cosine squared x over 1 minus sine x times cosine x. Okay. And now we need to look at that second fraction, sine x over cosine x. We need to multiply that by the quantity 1 minus sine x. So we're going to subtract sine x times the quantity 1 minus sine x all over 1 minus sine x cosine x. So now we have a common denominator. We can write this as one fraction. So this is going to be equal to cosine squared x, and I'm going to distribute that sine x through to each term, minus sine x, And now we have subtracting a negative value, which is actually going to be plus sine squared x, all divided by 1 minus sine x times cosine x. The numerator simplifies down really nicely because cosine squared x plus sine squared x, again that's our Pythagorean identity, so that simplifies down to a value of 1. If we add those two terms together, is equal to just 1 minus sine of x, all divided by 1 minus sine x times cosine x. Again, if we look, we should see we have two things in common, a 1 minus sine x and a 1 minus sine x. So we're left with 1 divided by cosine x. Cosine is the reciprocal of secant, so that simplifies down to secant x. So again, we started with something that looks fairly complicated. We had two fractions. If we use trig identities, that simplifies all the way down to just secant x. Example 6, find all values of x from 0 to 2 pi that solve cosine cubed x divided by sine x equal to cotangent x. Okay. First, remember one of the things I recommended earlier on, one of the strategies, rewrite everything in terms of sine and cosine. So we can rewrite this as cosine cubed x divided by sine x equal to cotangent, we can write as cosine x over sine x. So if I would take and multiply this side by a sine x and multiply this side by a sine x, multiplying by the same value to both sides of the equation, notice sine x cancel out, sine x cancel out. So all we're really looking at is cosine cubed x equal to cosine x, which if we're trying to solve, I want to set this equal to 0. So if I subtract cosine x to the other side, we get cosine cubed x minus cosine x equal to 0. Looking at those two terms, it should be easy to recognize that they have a cosine x in common. So that would leave us with cosine squared x minus 1 equal to 0. Again, we're going to use that Pythagorean identity we've been using a lot. If we take sine squared theta minus cosine, or plus cosine squared theta, and we know that's equal to 1, if we rearrange that formula a little bit, that value inside the parentheses, cosine squared x minus 1, is equal to negative sine squared x. So we have to be a little creative in figuring that out, but it's just rearranging that main Pythagorean identity. So this implies that cosine x is equal to 0, or that essentially sine x is equal to 0. Yes, it's minus sine squared x, but if we divide it by a negative 1, if we take 0 divided by a negative 1, that's just 0. If we take the square root of sine squared x to both sides, the square root of 0 is still 0. So negative sine squared x equal to 0 is essentially setting sine of x equal to 0. Looking at these and what we started with in the beginning, remember we started with sine of x in the denominator. So we can ignore where sine of x is equal to 0. Because those are in the denominator, it would be undefined. Those values don't even matter. The only values we're concerned with is where cosine of x is equal to 0. So we're going from the interval of 0 to 2 pi, so all the way around the unit circle. Think about where cosine is equal to 0. Where are the x values 0 on the unit circle? Should recognize or remember that those values would be pi over 2 and 3 pi over 2. So those are the two x values that if we put in there would make our original equation true. Last example, example 7. Find all solutions for the equation 2 sine squared x plus sine x equals 1. Okay. Another strategy, I know I've said that multiple times, another strategy we can use in order to simplify the process is I'm going to let sine of x be equal to y. The reason I would do that, if I let sine of x be equal to y, I can rewrite this as 2y squared plus y equals 1. Okay? And if I want to set this equal to 0, 2y squared plus y minus 1 equals 0. Essentially, we're trying to solve a quadratic equation. After we get the quadratic equation solved, then we'll put that sine of x value back in. It just makes the process a lot easier to simplify. And this will factor into 2y minus 1 times the quantity of y plus 1 equal to 0. So now I'm going to set each of those factors equal to 0. 2y minus 1 equals 0. If we simplify that, y equals 1/2. And if we set y plus 1 equal to 0, we know y would be equal to negative 1. So essentially we're trying to find, now I'm going to substitute it back in, where sine of x is equal to 1/2 and where sine of x is equal to negative 1. So we're going to be looking at our unit circle, finding where those values occur. The values where sine of x is equal to 1/2 are pi over 6 and 5 pi over 6. And the value where sine is equal to negative 1 is 3 pi over 2. So those are the three values for x that if we would put those into this original equation would make it true. Okay, I'm warning you right now, these problems are not going to be easy. You're not going to be able to figure out how to simplify or solve a problem the first time. Okay, you're going to have to try to look at which identity you might be able to use. Try using that identity. Chances are the first time it's not going to work. Okay, so be patient, stick with it. Eventually you'll find a way to simplify the problem. Okay, remember some of these strategies to use while you go through the process. Take out a common factor, rewrite the whole thing in terms of sine and cosine, get a common denominator, write it as a single fraction, and like we did in the last example, replace sine of x or cosine x with some variable. Okay, remember in that last one, replace it with the variable y, then we could solve that using basics of quadratic equations. Okay, so be patient, go ahead and get started on the homework.